Okay, so the back of your paper is f of x continuous at x equals 2 for the following functions. This is going to be similar to determining if the limit exists. They're kind of asking the same thing. So if we plug in 2 for a in that function, for the left side, we would be getting 3, and for the right side, you'd be getting 4 minus 1, which is 3. Okay, so they are going to be continuous because they have the same value on both sides. So yes for A. B is, we're going to plug in 2 again, so we'll have 2 plus 1, 3, and then 2 minus 1. 2 times 2 minus 1 is also 3. It's the same thing as A, but we have one has a less than 2 and one has a greater than 2. We have nothing that's equal. Okay, so the limits on either side are the same though. So limit as x approaches to left equals limit as x approaches to right. So therefore, yes, these are continuous. Okay. And then let's look at C. So if we plug in 2, we're getting 3. For the left side, 2 squared is 4. And then we also have 3 again because we've done that. This one is not going to be continuous though, because obviously we have a jump right here. It goes from 3 to 4 to 3. And we would have to pick up our pencil if we were drawing that graph. So not continuous, no. Okay, so there are some types of discontinuities when your function is not continuous, okay? Let me see if I can focus this a little more. There, all right, so a removable discontinuity, if you look at the example, you just have a hole in the graph. Okay, so that usually happens when there's a rational function whose common factors cancel, or the numerator and the denominator have common factors, okay? That's gonna leave a hole in your gap, excuse me, and in other words, your limit of f of x does not equal f of a at that point, okay? There's gonna be a little hole, and there may or may not be another point. It could even be open right here, and that's still removable, okay? Second type is jump. That usually occurs when you have a piecewise function. Piecewise function. Okay, which actually part C right here would have been a jump because it goes up to 3. You have one part of a function, a line going up to 3. Then your point is at 4 at x equals 2. And then your other part goes to 3 also. Actually, it'd be a different line, but yeah, that's a jump discontinuity. Okay, so i.e. the limit from the left and the right do not equal each other. Okay. Next, so infinite discontinuity usually occurs when you have a vertical asymptote. Okay, and then what happens when we have a vertical asymptote? I.e. a factor is in the denominator once you've canceled all the common ones, okay? And remember, we set that factor equal to 0 and solve. That's where your vertical asymptote is, okay? Or in other words, that limit goes to infinity. That would be infinite discontinuity. All right, so the last thing for this idea is to look at these 5 examples and determine which type of discontinuity is happening. So you have removable, you would have common factors canceling, piecewise function would be jump. And then at infinite discontinuity, you have a vertical asymptote. All right, so let's look at number 1. If we were to plug in 2 to the left side of this function, we would get 5. The right side would be 4. So that is definitely going to be a jump discontinuity. We have a piecewise function that equal 2 different values on either side. Okay, and it's at x equals 2. That's your jump. All right, next. So if we plug in 2 to these piecewise parts, okay, if you look at the numerator, the top, or not the numerator, but the top function, and we plug in 2, we'd be dividing by 0. Okay, so we're gonna have to simplify that more. So I'm looking at the first part of this piecewise function. That's x plus 2, x minus 2, and then x minus 2, okay? And you should notice this is one type of discontinuity we were talking about. All right, so those would cancel, and x equals 2 is what it would simplify. Sorry, x plus 2 is what it would simplify to. Okay, and so if we were to plug this in and not get the same value, that would look like one of the removable discontinuities because we had a common factor cancel, okay? But let's see, so this would simplify to x equals, or x plus 2, sorry. I'm plugging in 2, you're gonna get 4. Okay, and then it tells me that, so this actually is a whole at x equals 2. Okay, but when we put in this other chunk of the piecewise function at 4, it fills that hole in, okay? So since these are the same, this is completely continuous, okay? But if we weren't given this bottom part here, it would have been a removable discontinuity. So the top thing makes a hole in the graph at x equals 2, at 4. There's a hole in the graph, okay? But what this second part of your function, piecewise function, does is it goes and fills that hole in. So it makes it continuous now. Okay, so that's kind of an example of 2 types of discontinuity there, okay? Even though the whole thing ends up continuous. Hopefully that makes sense. All right, number 3, we have 5 over x minus 2. As you can see, the denominator, if we set it equal to 0, would be x equals 2, okay? And so that would mean you have a limit going to infinity at x equals 2, all right? So limit as x approaches 2 of f of x, and then you would pick a value and plug in to see if it goes to positive or negative infinity. So if we picked 3, it would be positive, okay? That means we have an infinite discontinuity, okay? All right, 2 more. Now number 4, we have 2 polynomials, or 2 trinomials that we need to factor and then see what happens, okay? So this one's really important. I would start it and make sure you know what to do here. Okay, so we're gonna factor the top and the bottom. X squared minus 8x plus 15 should be x squared minus, x minus 3, x minus 5. Okay, x minus 3, x minus 5, all over x minus 5, x minus 1. Okay, so those 2 factor to this. Hold on one sec. All right, and so our common factors are x minus 5. Those are canceling. Okay, so that is actually 1 one type of discontinuity. That means there's a hole in a graph at x equals 5. Okay, and that is a removable discontinuity. Okay, so it's not like our denominator equals 0 at x equals 5 and it's going to infinity, all right? However, when you cancel those common factors out, that creates a removable discontinuity. All right, so from here, we're left with x minus 3 over x minus 1. Nothing else cancels, so now you can see if we set that equal to 0, there's going to be a vertical asymptote here. The limit's going to go to positive or negative infinity, okay? So we also have an infinite discontinuity at x equals 1. So there's two types of discontinuity on this graph. Okay, we'd have a hole here at x equals 5, and then vertical asymptote at x equals 1. Okay, last one. We really are just testing the left and the right sides and see if they equal each other, okay? So for the first one, at -1, we need to look at those values first, see if they match up, all right? So I have 1, and then if I plug in -1 for x here, I would also have 1. So it's continuous at x equals 1, -1, excuse me, -1. All right, so that's good there. Okay, so let's look at 0 now. So if I plug in -0 to the left side, I'm getting 0. And if I plug in, well, that's just 1 on the right side, okay? And then at 0, it's 1. And then on the right side, if you plug in 0, it's 0. So for x equals 0, on the left side, we're getting 0. The right side, we're getting 0. But at f of 0, it's 1, all right? So that is a removable at x equals 0. Okay. All right, so why is it removable? Because the left and the right side equal each other. So they're gonna be like this. And then, but actually at f of 0, it's open. So, or it's not at the same value, okay? That's a removable. So these are going to 0, but f of 0 is 1. All right, it's a little different than jump. So let's look at the 1. So if I plug in 1 here, I'd get -1. And then for the other side of 1, it's 1. So this is actually a jump. Oh, the 1 is closed, the -1 is open. This is actually creating a jump in the graph, not just a hole, okay? So removable, it was the same on either side, but f of 0 is not the same. That's a removable discontinuity. A jump, you're getting two different values from either side. So it's actually creating a jump in the graph, not just a hole above. Okay, that's it.